I asked Didier Paillard, who is really the specialist for that, to give us some overview of the climate model, and especially what he's been doing is small climate model in order to, not GCM, not big GCM, but he may speak of that. I don't know if he will speak of that also. But the idea is to have the transfer from the insolation forcing to climate. In this session, we are going back to climate and to eventually ice, mostly ice output. So Didier Paillard is at LSCE, also in the Institute Pierre-Simon Laplace. LSCE is the Laboratory of Science, Climate Science and Environment Science in Orsay. And we've met many times over the past 30 or 40 years, I don't remember. And I'm very pleased and eager to listen to him now. So Didier, it's you can start now.
Thank you very much, Jacques, for inviting me to give this talk. It's really a pleasure to be there. Well, actually in my office, but to present this to you. I will start with a historical point of view on astronomy and climate, and I will discuss two different things actually. First, ice ages, because that's really the starting point of the questions between climate and astronomy. But I will also continue in a second part on discussing the link between astronomy and carbon, because I think this is quite a new and important perspective on the links between climate and astronomy. First, maybe I should say that climate is not a well-defined word, and for different people it means very different things. I will not talk, for instance, of temperatures, precipitations, and things like that. I will mainly focus on these two objects, which are ice sheets and global carbon. And if you think of the temperature, actually the temperature or the precipitations on Earth, they depend on astronomy, of course, on the presence of ice sheets, on the carbon dioxide concentration, and on many other things. But these three elements, astronomy, ice, and carbon, are the three main boundary conditions for GCMs. So we really need to understand these three objects before starting to discuss regional climates and so on. So climate, again, it's not so well defined. So I will try to restrict myself to ice ages and carbon cycle. Okay, so if we go a bit back in time in the history of science, it's interesting to note that before the discovery of ice ages, the idea of climate change was not really there. The idea was maybe the Earth underwent a very slow cooling since its formation. And you have this kind of picture to summarize the point of view of scientists at the beginning of the 19th century. So probably a hot origin for the Earth and a slow cooling. And it's interesting to note that many point of view that are still present in the general perception of past climate is coming from this time. I mean, many people think that the Carboniferous was very warm, for instance, because it was described very warm at that time, and it's still there in the general view of many people. So it's interesting to try to break these old ideas. This was, of course, also the starting point to try to compute the age of the Earth, as you probably know, from the cooling of the Earth. In the middle of the 19th century, then people started to discuss about ice ages. So I will not go into the details. Probably many of you actually know much better than me this part of the story. So the discovery of erratics in many regions in the northern Europe, in the Alps. And you have an example of in the French Alps of the trajectories that can be reconstructed from these erratics. And it was already obvious in the 19th century that it was not the only way to transport such big blocks was to do it by ice. And you also have the U-shaped valleys and so on, which are very characteristic of ice ages, and also the existence of moraines. All these put together were the first evidence of a different climate, which did not fit in the picture presented before of a slow cooling of the Earth. And so this was heavily discussed in the 19th century, and the only explanation was to explain all these phenomena with the presence of ice, as you know today. So this is the start of a story which is still there today, which says that climate is not constant through time, or that the history of climate is much more complex than what people thought before. So this is the start of two physical theories of climate: the astronomical theory and the theory based on the carbon cycle. And here you have a few famous people who were at the beginning of these different theories. You probably know several of them. Concerning the astronomical theory, you all heard about the Milankovich theory, but earlier theories were proposed in the 19th century, already at the beginning of at the same time with the observation of the ice ages. It's interesting to see that these two ideas were already present. Ideas were usually very separated, so either you were on one side or on the other side. And there are very few exceptions of people who tried to get the best of the two theories. And Niels Ekholm is one such exception. So it's quite interesting to read what he wrote. What I want to say, and maybe to insist a bit on that, is that the causality in these different kind of theories is quite different. First, there are still today many people who misunderstand the astronomical theories and who think that insolation variations modify the global climate and then eventually the extent of ice sheets. This, of course, does not work. And this was clearly stated in the 19th century by astronomers who computed that the net effect, the net energy input of the Earth basically does not change sufficiently, so it's very, very small, and it cannot change climate. You cannot change climate in this way. So the naive theory does not work. And the only input of astronomers to the ice age theory is to say that it does not work. So astronomers say, well, we make the computation of the energy input, and you cannot change climate with that. The astronomical theories, as we understand them, works the other way around. Insolation will modify local and seasonal temperatures, mainly above the ice sheets, because that's the region of interest. And eventually will modify the size of the ice sheets, and the ice sheets will eventually modify the global climate. So as you can see, the causality is a bit more complex. And that's, I am teaching quite a lot, and that's a difficult point. I mean, people very often misunderstand that. And the geochemical theory is more straightforward in some way. You put more CO2, this warms global climate, and you have an ice sheet. You have some implications of the ice sheets. So that's why at the end of the 19th century, you have only these two theories left, which I will call the astronomical ones and the geochemical one. And astronomers who basically say, well, it's not possible. So these two theories were developed on one side by established scientists. They were usually more in favor of the geochemical theory. And again, the astronomical theory was mostly developed by science amateurs. And I think it's very striking when you look at the papers that most scientists, well, established scientists, those who had a teaching position or academic position, they were not so much in favor of the astronomical theories. And it was mostly built by, well, the first mention of that is Adhemar. Adhemar was a math teacher. It's difficult to find any information on him, actually, because there's very few documents. The other famous guy was Kroll in Scotland, and he made many different activities. He was selling insurances. He was a pastor. At the end of his life, he was a librarian at the university, and he started reading books on geology, and he wrote some papers on the astronomical theories. Milankovich was an engineer who built bridges and dams, and again he decided to change activities and to try to understand climate. So this is something that really strikes me, that this question was not basically overlooked by most of the scientific community for quite a long time. Okay, so concerning the CO2, so I will just mention that, but you probably know that quite well. Of course, the idea that CO2 has some effect on climate arises from the discovery of ice ages. And I like to mention this citation from Arrhenius, who says in his papers that he would certainly not have undertaken these computations if not the discussion about ice ages at in the Physical Society of Stockholm. So once again, the discussions near the coffee machines are very, very important to develop science, and this is a good example. So why a chemist would make a theory on geological evolution? That's because there's some interesting into that when discussing with colleagues. And again, I'm not sure this would be possible today when you have a strong separation between different fields, and physicists in one building, geologists in another building, and so on and so on. This was not the case at that time. Concerning Niels Ekholm, I have a special mention for him because he was both in favor of the geochemical theory of ice ages, so he insisted a lot on the role of CO2, in particular on the future role of CO2 on climate, so present-day situation. But also, he was also very aware of the role of astronomy, and in particular that the decrease of obliquity should lead us into a new ice age. And therefore, he was very optimistic, and he said that, well, thanks to the burning of coal, we will avoid the next ice age. And I will also say a few words on the first astronomical theories. And the theory of Adhemar is very funny, actually. So it's very interesting. He tried to explain everything with gravitation. And in his view, if you want to explain not only ice ages, but many other things, so why there are more oceans in the south, for instance, and more continents in the north, why you have floods, marine fossils and mountains and so on. So all this would fit into his simple view of ice ages, with periodic ice ages, with a huge ice building either on one hemisphere, either at the South Pole or at the North Pole. And this would displace the center of gravity of the Earth. And this would displace the whole ocean, either on one hemisphere or on the other hemisphere. So that's why his book is called Révolution de la mer, which is revolution of the ocean in some way. Again, it's a very not realistic at all, of course, but he is the first one to explain the role of astronomy, to suggest that astronomy is the main forcing for ice ages. And the successors, in particular James Croll, they refer to him as providing the idea of the astronomy being involved into the building of ice on one hemisphere or the other. So the idea of Adhemar was to insist on the duration of seasons. He noted that first, the duration of seasons is not the same in the northern hemisphere and the southern hemisphere, and this changes with precession, and therefore, if you have a long winter, then maybe you could have more probability to build an ice sheet, and this would change every 20,000 years from every 11,000 years from one hemisphere to the next, to the other. So this was taken in a more scientific way by James Croll, and we insisted a lot on the role of eccentricity. And in the view of Croll, it could work only if the eccentricity of the Earth was larger. Therefore, according to Croll, the glacial ages would only be linked to high eccentricity, which is actually not true. But the main interest of Croll is that it puts this idea into the scientific community. Actually, Adhemar simply wrote a book and not a scientific paper, and the first to write really scientific papers was James Croll. This was discussed heavily in the 19th century, and I have taken here a copy of a paper from Murphy, who was part of the discussion, and Murphy contests the idea that the winter should be the season who is responsible of ice ages. And he says that mild summers should be much more important into the building of ice sheets. So Murphy is the first to contest this idea of the role of winter. And in fact, there's a sentence in his paper which is very interesting, because it tells us why people in the 19th century were discussing this role of the different seasons on the ice sheets, like the summer or winter. And I think the answer is in this sentence from Murphy, which says there's one fact of physical geography which seems to support Croll's, so the theory of ice ages being linked to long winters, and it's the presence of Antarctica. In other words, the mistakes of the geologists of the 19th century was to try to understand Antarctica as a result of an ice age theory. So to put too much things into the theory. And of course, this is not correct. But the origin actually is there, and it's from Adhemar. So these mistakes is the original mistakes of Adhemar, trying to have an anti-symmetrical theory of ice ages. So the fact that ice ages are either anti-symmetric or symmetric, that's the main difference, I would say, between the theories in the 19th centuries and theories in the 20th century. The main progress made by Milankovich was first to compute numerically the insolation from the astronomical solutions, and also to put forward this idea that actually the obliquity, so the symmetrical forcing of both hemispheres, is the most important forcing on the ice. Okay, so maybe I can show that as an illustration. So the dominant role at high latitude is linked to obliquity forcing, and and it's symmetrical. So if there's Antarctica, it's not linked to astronomy, it's linked to the position of continents, of course. Okay, so this is the computation of Milankovich concerning the northern hemisphere, well, the high northern hemisphere summer insolation. And as you can see, what Milankovich did was simply to put the known ice ages at the minima of insolation. So and to say that, well, it seems to work reasonably well with other evidences. First, his computation is not completely different from what we know today, at least on the most recent part. So indeed, you have the insolation minima, which are located correctly. And the discussion of Milankovich was simply mainly a stratigraphic one, just to say, well, we just have ice ages at those locations. And this is a lot in favor of an astronomical theory. I think the problem with Milankovich was he had no record, no continuous record of ice ages. Things changed quite a lot with marine sediments. With marine sediments, you could start to have a continuous records of climate. And then you could start to not only discuss some specific events, but try to look at the curves themselves and the minima and maxima. Here, there's also an interesting story with the famous work of Emiliani. So Emiliani gave the numbers of the different marine isotopic stages, and there are many students who don't understand why there's an isotopic stage 3, for instance. So indeed, in 1955, when he published his first isotopic curve, he tried to correlate it to the astronomical forcing. So according to Milankovich, the main forcing is linked to obliquity, and therefore the curves you could get associated with ice ages, summer insolation at high northern latitudes, would mainly be driven by obliquity. And when he tried to put his data in front of this curve, so first it looks reasonably well, but the problem, of course, is the chronology, the stratigraphy, the chronology. And if he had some type points, if he had some ideas of the chronology in the first part, therefore stage 1, 3, 5, in order to correspond to the obliquity forcing, the other ones were rather arbitrary. And actually, if you look at the publication later on, you note that the 41,000-year cycles that he described in the 1950s were actually 100,000-year cycles. And so you get into this paradox that you have both a confirmation of the astronomical theories, because you find a strong astronomical signature in the records, but also a big problem because the expected periodicity is not the one you find. You find mostly a 100,000-year periodicity, whereas the predicted one by Milankovich was mostly 41,000 years. That's why the title of the famous paper of Hayes is that the Earth's orbit is a pacemaker of the Ice Age, but not necessarily the ultimate cause. I mean, there's something missing into this story. So the dominant cycle is not directly linked to the forcing, but is driven in some way, quotes, by eccentricity, and he says that he doesn't know what is the link between eccentricity and the ice ages. So that's the start of the question mark, which is still not completely resolved today, which is the origin of this 100,000-year cycle in ice ages. So as a short summary of all this story, we know have a much longer records. We know that we have the start of quaternary glaciation somewhere 3 million years before today. And indeed, it starts with 41,000 year cycles. So Milankovich was right. That's the true prediction of Milankovich is indeed correct between 3 and 1 million year. And this was not discussed in the 70s because we did not had access to the chronology, to precise chronology there. And people focused mostly on the problem of the Milankovich theory, which is the 100,000 year cycle. But in some way, before 1 million year, the prediction of Milankovich is really correct. Okay, so what can we say about this question? So you can summarize the Ice Age problem with this question mark. How do you get from the insolation, the input? So you could add also what kind of input, what is summer, what latitude, but what? Let's assume that summer insolation is a good starting point, and you want to deduce from this curve by some physical or some mathematical process something which looks like that. So try to decipher what you can say about this in some way. Which way? So there have been many attempts to do that with some simple mathematics, some simple physical ideas. Interestingly, the first one in 1974 is, again, not a scientist, it's a journalist who was surprised to discover that there was no mathematical prediction for ice ages. There was the data, there was the result, but the Milankovich theory did not predict anything. So he thought that maybe it would be interesting to make a prediction, just write a simple model and try to use the astronomy, a simple model to predict what we should see in the record. Interestingly, it works reasonably well. I have a few slides on that just later. And this was taken further but by other people. So a special mention for Imbri, who published also a very simple model just after Calderon. And this model was used quite a lot for cyclostratigraphic purposes, trying to link oxygenating records with some model, with some astronomical forcing. And there was also attempts to build more complex model involving chaotic systems, for instance, more complex model trying to involve also the carbon cycle. I will not comment on that, but you understand that this question of how to produce 100,000 year cycles with some physical principle, it was not so obvious. So a few words on the first one, the Calderon model. So it's the most stupid model you can think of. You just say that the change of ice volume is directly proportional to insolation. So the more insolation, the more melting, and so on. The only subtlety is to use a different coefficient, whether it's melting or whether it's growing. And if you do that from this insolation curve, you get this ice volume. This is an exercise I give to my students, and they are happy to compute ice ages from the insolation. Very easy to do. So he did that on a pocket calculator. And if you look at his original curves, well, it doesn't work so well. It works reasonably well in the first part, I would say. But then it's getting more and more, the comparison is getting less favorable with the data he had at and at that moment. But interestingly, when you use today's datation, today's chronology for quaternary records, you notice that actually his model was reasonably good, and in particular, he did predict correctly the transition, the timing of specific terminations, for instance, interglacial 19 and Bruns-Matsuyama reversal. With his model, is predicted at about the right date. So it's interesting to note that a posteriori, this kind of stupid model was able to predict something before it was measured. So why does it work? And then you can try to understand why is it working so well in some way, at least on the timing, not necessarily the shape, but the timing of termination is reasonably well reproduced with this kind of simple model. And if you want to understand why, you can think a bit about this model, and you understand that actually it does predict well, not the terminations, but the glacial maxima. And it does predict the glacial maxima because glacial maxima and the 100,000-year cycles are linked to not to the insolation minima, but in fact to the amplitude modulation of the insolation, and to the fact that some insolation maxima are much smaller than others. And this is indeed reasonably well correlated with the isotopic record. And this is why...
Excuse me, Didier.
Yes?
I don't understand exactly what is the prediction. You have the red curve is the insolation.
You mean from
on the next slide?
Yes.
On this slide, the red curve is the insolation. The blue curve is the observed delta 018.
Yes.
So what is the prediction? Where is the prediction curve?
Here, there's no prediction here. I was talking about this one.
Okay. Okay.
This paper in 1974 by Calderon. This was his model. So the middle curve was his model, and the top curve was the data available at that time. And the comparison between his model and the data was, let's say, not perfectly correct, especially in the oldest part. And it turns out that, in fact, if the comparison is not very good, it's not because of the model, it's because of the data. And if you use the data, the present-day chronology, so if you replace this data curve with the current chronology, we would say, then the model works much better. So in some way, this very simple model predicted correctly the 100,000-year cycles before, at least in this oldest part, before they were well dated. So that's something I think is interesting from a scientific point of view, is to have models that are able to predict something, not only models that are able to reproduce what we know, but also able to say something about that has not been put in the model as an input of the model. That's what I wanted to say. And then the question is, why? Why does it work? And it works because of this amplitude modulation phenomena. It works, you can try to analyze the curve and say why I do have a transition at that point. In fact, I don't have, if you look at the model results, so the bottom curve, the 100,000-year cycle you see is not actually in the transition, it's in the glacial maxima. So the model predicts the glacial maxima reasonably well. And why does it predict glacial maxima that are larger than others? Because of this amplitude modulation of the forcing. So this suggests that the key the key mechanism to get 100,000 year cycles is simply to extract the envelope, which is very simple and very natural. So you have to extract the amplitude modulation of the forcing to produce 100,000 year cycle.
So Didier, are
Yes.
those arrows, are the arrows pointing to the peaks or to the inflection points?
Oh, it's just a visual way to associate the small maxima in the forcing with what we call terminations. Actually, you should point them towards the glacial maxima, not towards the association is with the glacial maximum. But this tells us that in some way, the 100,000 year cycle is not linked, is not caused by terminations, but by glacial maxima. So there's a strong link. Terminations are caused by glacial maxima in some way. So this is I think the key towards understanding the 100,000 year cycle is to try to extract the envelope. And one way to do it is simply to have lower insolation maxima, therefore larger glacial times, larger glacial periods. And this is linked in some way to terminations. Okay, so when I was a PhD student, so some time ago, I started to play with that. And at that time, there was also the idea of thermohaline catastrophes, you know, the Cenozoïc events, the Heinrich events in quaternary records, and therefore the idea of multiple equilibria and thresholds and historics. And I thought this should be also quite useful to put these ideas into the context of ice ages. And indeed, if you do that, if you build the same kind of simple linear model, but with thresholds, you get a very good agreement with the data. So this is some kind of it's more some kind of data analysis than some kind of physical modeling, I would say. I start with the data and try to extract the mechanism, the physical mechanism that can explain the observation. I just try to discuss whether it's physically reasonable or not. But the idea is to start really from the data and some physical ideas. So if you have a model with varying insolation and the thresholds on the system, so in my paper I put the threshold into this way, but actually you can do something simpler than that. And you need basically two ingredients, which are, well, actually you need basically one ingredient, which is to say that terminations, again, are associated with glacial maxima. This is a key point. And if you want to build this kind of simple model, the key mechanism, so yes, I have a simpler version here. The key point is to switch from one mode to the other. So to switch from a glaciation system, which will be more or less linearly linked to insolation, but with a tendency towards more ice, and a deglaciation mechanism which starts because of the glacial maximum. So this is what we can call a relaxation oscillator, something like you know, in electrical system, you can charge a condensator, and then discharge it rapidly, and charge it slowly and discharge it rapidly. And the trigger for this to work is to get through a glacial maximum. If you assume that in mostly a linear way with this kind of simple relations, you get a reasonable agreement with data.
Just a question here. I don't see the ice volume in your equation.
It's V. V is the ice volume, yeah.
But
so P is the ice volume.
What is the difference between I And V.
I is the insolation and V is the ice volume. So I is the input,
Okay, okay.
V is the ice volume, tau are constants. And so you need actually three different time constants here. And a threshold mechanism.
Okay, I understand. Yes, so keep going.
And when you plot the results, and you can just play rapidly with the numbers. There's not so many numbers. You get rather easily this kind of results, which are again reasonably good, I would say. You can of course try to find some best solution, but we didn't try to do that in this paper. In this paper, we just tried to look at the insolation forcing much more than at the ice mechanism. And the question was to look at whether it's possible with a different kind of insolation, summer insolation forcing, to reproduce the same mechanism. So is it robust versus the forcing? As you may know, summer insolation is a bit vague. And summer insolation, according to Milankovich, is the integral of insolation during the 6 months, closer to the summer solstice. Whether today we often define summer insolation at the summer solstice exactly. It makes a difference in terms of spectral content, for instance.
So the insolation here is not the instantaneous insolation.
Both. Actually, you have two experiments. One with the summer solstice insolations. That's this one. I don't know if you can see my arrow.
Yes, we can see.
Yes. So this one is the one using the summer solstice insolation. And this one is the one using the Milankovich caloric seasons, so integrated over 6 months.
But you could use directly the insolation as a function of time without making any average, without making anything. But it's not what you are using.
You need to select one season. That's the Milankovich theory. You need to say that
the
insolation are sensitive.
Summer.
Sorry?
It's sensitive to the insolation in summer, for example. Also.
Yes, and you need to specify what is summer.
Okay.
And according to Milankovich, the number you need to use is the total energy between during 6 months, the summer half year, he says. When you do that, you have more spectral power at the obliquity, in the obliquity band. If you use a definition that is more restricted to the solstice, you have more power in the precession band. And the curves are not exactly the same. And we just wanted to check whether it matters or not for this kind of model. Actually, it does matter a bit, but not too much. The main conclusions are stable versus this kind of input. This kind of model was also used. Actually, it's a paper which was published last week, I think, from Etienne Legrain. He also uses the same kind of model, trying to investigate whether the mid-Pleistocene transition is most likely caused by either a gradual or an abrupt transition. So you can use the model and try to compute the best fit with the data. And with actually the critical parameter in all these models, it's again the threshold. The threshold you use to trigger the deglaciations. That's the critical point. So this equation here is what is the threshold of which will trigger the deglaciation, and it's a threshold on the ice volume itself. And you can make Monte Carlo simulations and trying to get the best fit. And according to this paper, the most likely model, if you assume that the probability of the model is comparable to the probability of the parameter space, which is also a philosophical question, then his conclusion is that the gradual evolution of the parameters describes more in a better way the mid-Pleistocene transition. Okay, so you can play quite a lot with this kind of simple models, and I think it's useful to get some insight. Okay, so this leaves us with two key questions, I would say. The glaciations are triggered by glacial maxima. That's a robust result. But what is the triggering mechanism? And also there's a trend towards larger cycles. And why? And I tend to believe that the CO2 has some role in these 2 points. So I think I will skip that. I think CO2 has some role in the glaciations, mainly for timing reasons. So CO2 is increasing before the melting of the ice. That's an observation. So if you look at the causality diagram I showed you before, if you think of the Milankovitch theory, well, it works reasonably well, but not during terminations, because during terminations, the global climate is warming before the melting of ice sheets and not after the melting of ice sheets. So it doesn't work in the framework of Milankovitch theory. It works better in the framework of the CO2 theory, because indeed global climate warms before the melting of ice sheets. This is much more correct versus what we know from data. Okay, so you can try to do that in models. I will not insist on that. Carbon and astronomy. Okay, so there's a link. Climate, it's not only temperature, it's not only ice sheets, it's also precipitations and many other things. And I like to show this, to present the question of the Green Sahara to explain that. And we are very dependent on precipitations, not only on temperature. And this has, there were huge modifications in hydrology linked to precessional forcing in these kind of regions. And this has some implications, for instance, on the preservation of organic matter in some regions. Again, one of the best example may be the subtropical events in the Mediterranean Sea. When you have more precipitations, you have a change in the way you can preserve organic matter in this kind of regions. And you get very nice stratigraphic sequences of organic matter preservation. And this is certainly one of the best examples of the astronomical forcing on the system. Interestingly, you can do that also with isotopes. And with isotopes, you can find in the reports, and I think many of you know that better than I, you can find many astronomical signatures in the C13 of marine isotopes all over the world in many different regions, and it seems to be quite global. This is also a very useful stratigraphic tool because you find nice frequencies. And okay, so I will not insist on that, and I will directly go to, can we make simple models from that? So my simple view of the system, again, is to consider that we have fluxes between the solid Earth and the ocean atmosphere system, mainly three kind of fluxes. So the input from volcanisms and two sinks, one linked to carbonate precipitation and the other one linked to organic matter preservations or oxidations. So the green arrows can be both ways. So currently it's mostly a preservation arrow, but I am only interested in the net. It can be negative. That's what I want to say. So from that, you can very easily compute equations, not only for carbon, but also for C13. And you can, if I am doing that, it's because when you see large C13 variations in the system, it it's certainly it is much more easier to explain that in terms of organic matter preservations than in terms of any other thing. So organic matter preservation is certainly one key to understand these cycles. The classical way to discuss long-term carbon changes is in terms of silicate weathering, and you probably know the mechanism of the Earth's thermostat, which says that among these three fluxes, the weathering depends on climate and therefore on carbon. And if you assume that silicate weathering is an increasing function of carbon, then you have a thermostat, so a system which has one stable equilibrium, and this is often called the Earth's thermostat or the Walker feedback, or this is supposed to regulate the climate of the Earth. When you look at C13, for instance, over the last few million years, you get the feeling that these fluxes, well, at least the organic carbon fluxes are not constant through time. And it's interesting to try to get some insights into that with simple models. So first, you can try to put some astronomical forcing into this burial term, and then quite easily you can translate that into C13, and actually it works reasonably well. You get this kind of curves here in the middle compared to the data, so the gray shaded area. So you have the 400,000 year variations, which are indeed easily explained by the astronomical forcing if you use this link of organic matter preservation. You can also try to compare that with the CO2 record on this time period. Well, actually, we don't have CO2 record so much, and we know that we need something else. So you can explain small variations of CO2 with that, but probably not large variations. Nevertheless, there's some connection between these C13 changes in the record and the climatic changes we see even on the more recent quaternary timescales. So, for instance, the mid-Pleistocene transition is associated with the maximum in C13 about 1 million years ago, and what we call the mid-Bruns transition from smaller CO2 variations to larger CO2 variations. It is also associated with a C13 maxima. So we have the feeling that there's a strong connection between the shifts in climatic regimes and the C13 curve, which is again quite intriguing and interesting. Okay, so I will not discuss that. Yeah, I will not discuss that. Well, maybe one word, just to say that if you want to reconcile a bit things, you can try to go a bit further. One intriguing point over the last million years is that the cycle you find are more 500,000 year cycles and not 400,000 year cycles. Of course, there's only two, so it's a bit difficult to be completely definitive, but still, you can see these two cycles here, 1, 2, and it's not 400, it's more 500. So why? It's strange. It's not compatible with astronomy. If you want to explain that, you need to find some perturbing mechanism. And I think it's quite easy, because that's precisely the time where you have ice sheets and you have large sea level variations. Therefore, if you want to reconcile this carbon burial mechanism with what we know from astronomy at 400,000 years and what we get from the data at 500,000 year cycles, you need to perturb something, and if you assume that organic carbon preservation occurs on continental margins, then you get probably the idea that continental margins are strongly perturbed by sea level variations during the last million years, which is reasonable with sea level variations associated with quaternary ice sheets. So I think it's a strong indications that something occurs on the margins, and I think I believe the margins are organic matter deposition on margins are responsible for this mechanism and for this mismatch during quaternary times. That's my point of view, at least. Can we use that a bit more in older times? So I made I did a small game, I would say, using the long-term C13 records from, you know, the Zakos stacks, but also the older stacks from Friedrich in the older Cretaceous. And if you assume that this kind of relation is true, if you further assume that the astronomical variations at 400,000 years are stable through time, and that the mechanism which links them to the C13 record is stable through time, so a lot of big assumptions, then you end up with the idea that C13 variations at 400,000 years should be inversely proportional to the carbon reservoir. So the more carbon you have on Earth, the smaller the C13 variations. So if you want to estimate the size of the carbon reservoir, you just need to estimate the size of the C13 variations at 400,000 years. And this is what we did in this paper. And interestingly, it works. It's not completely stupid, because we get smaller C13 oscillations at some times. For instance, at the Eocene, the amplitude of the oscillations are smaller. Therefore, probably the size of the carbon reservoir is larger. And this is the kind of numerical computation you can get from that, which is not completely orthogonal, I would say, which shares many similarities with what we know from other records, from CO2 records, for instance. So I think that's one way to use C13 records in a more quantitative way to discuss carbon on Earth. And finally, I want to end up with some work we did on the long-term C13 cycles. As you may know, there are 9 million-year cycles in C13, and the question mark is whether they are astronomical in origin or whether they originate from something else. So they are very clearly visible in the Cenozoic. They also are visible in the Mesozoic, according to these two papers. And we need really a theory for that. There's some interesting thing occurring behind that. And always using the same framework, I would say, I think it's not reasonable to assume that organic matter preservation is a simple story. And if you make one simple assumption, say, well, instead of being a linear function of temperature, instead of being a linear function of forcing and so on, let's assume it's not linear, but maybe a step function, something which varies in the first time, something which decreases when you increase temperature, which is something we observe today. For instance, when you have more monsoons in the Himalaya, the net effect is to increase the oxidation of kerogens, so old organic matter in some regions that will be put into the system. So actually, if you increase temperature or carbon, maybe you will put more carbon into the system, so destabilizing a mechanism. And if you further increase temperature, then you can get many stabilizing mechanisms like producing more organic matter, decreasing oxygen content in the atmosphere, and so on and so on. So just assuming that you have a two-step story, not a one-step story, you can get a scheme with multiple equilibria. And when you have multiple equilibria in such a dynamical system, if you add, for instance, another variable, for instance, oxygens, interestingly, oxygen is controlled by the organic matter barrier. The more organic matter you are burying, the more oxygen you get into the atmosphere. And as a feedback, the more oxygen you have into the atmosphere, the more carbon you can oxidize. In this way, you can easily build actually an oscillator, an internal oscillator. And if you put the right numbers, you can get things which are in a reasonable range. So getting an oscillator which oscillates at 9 million years, it's not very interesting. You can do that probably in many different ways. The interesting thing is that when you had the astronomical forcing in the same way I did it before, then you get some frequency, some phase looking to eccentricity. In other words, the eccentricity will be able to switch the system, but not every 2.4 million years, but only one, depending on the parameters. It can occur either at the frequency of the eccentricity, so about 2 million years, or at the double frequency, about 4 million years, or at the triple frequency, and so on. So that's a mechanism to extract astronomical periodicities at a multiple of the forcing frequency. Of course, we didn't prove anything, but it's just I would say, a concept idea trying to get longer time scales from the installation forcing. I will stop here.
Thanks a lot. Yes, that was very interesting. And I'm sorry that you had to rush in the end. Thanks for this overview. So are there any questions, Paul?
Yeah, hi. So great talk. I very much enjoyed that. I have a question about your last point, and that is, of course, that the G4 minus G3 cycle that you refer to as, having multiples of to explain the 9 million year cycle, right? That in the Mesozoic, that wouldn't be, or we don't know. In some cases we know, but it's not likely to be 2.4 million years. So the 9 million year cycle shouldn't be 9 million years either.
Mm. I would say I would not stick too much to this specific model.
Oh,
there
okay.
are many things that works. So if you want to look for instance, at the result, the result of the model, so that's a blue curve versus the data, the blue. I wouldn't say it's really similar. Still, the idea of trying to find the right frequency of the record that you get in the record, trying to find the exact same frequency in the forcing, I think it's not the best strategy. I think you have many ways in the climate system, in particular in the organic matter preservation, which is, to say the least, a bit complex. There are many ways to build oscillators, to build some internal dynamics, and therefore, probably, I think it would be possible to have theories producing this kind of oscillations from forcing frequencies that are quite different. That's my point, I would say. And that's just an illustration of that.
In fact, I think it's very interesting. Your model is very interesting because I must say I don't buy the idea that there is a direct forcing at 9 million years think the power is not there in the solution. So there is nothing much. So it's quite interesting to think of the possibility, even if the model you present is not exactly the one, even if you show that something is possible in this direction. I think that's the idea, and that you could force at the 2.4 million year, and get some excitation, some response at an harmonic of this 2.4 million year using some physically relevant model. Is that what you?
Yes, that's my point. Yeah.
Yes.
In some way, it's not so much different from the 100,000 year problem I presented for the ice ages. In some way,
No, it's very different. It's very different because let me tell you because why it is very different. Because in the problem of the ice age, the envelope, so the main forcing term, the envelope of the precession, which is related to the insolation, is already the 100,000 year eccentricity term.
Yes.
So what you do basically with the ice model, with the ice nonlinear model, you recover this envelope, but this envelope is already there.
Yes, that's right.
Here it is different. You need a model that is excited, where the response is at the frequency which is not really present in the input signal.
In some way, because actually in this model, I get a multiple.
Yes, you get a multiple. You get an harmonic. It's excited and an harmonic of the input, but this harmonic is not has a very low power in the input signal. While in the eccentricity, the envelope of the eccentricity has the highest power. It is already the most, and if you see, this is something I made a wide audience talk 2 days ago, and I presented the effect of eccentricity. I just show that just compute the variation from perihelion to aphelion of a black hole of a black body planet, and the relative variation of temperature is the eccentricity. So it's the seasonal variation, which is the eccentricity. It's 5 degrees in the present situation, but it's 17 degrees in the for high eccentricity or for the highest eccentricity of the planet. So we have, of course, you mentioned the problem of the eccentricity, but it is when you compute the global eccentricity over 1 year, the average eccentricity over 1 year, the average insolation over 1 year, and the average insolation over 1 year varies as the square of the eccentricity, not as the eccentricity, while the seasonal variation varies as the eccentricity. So, okay. There is a question by Joseph Nar.
Hello, thank you for the
Can you present yourself, please?
Yes, sorry, I'm a PhD student from at LMD Paris, working on ice ages, but on planet Mars. So it's a bit, I mean, a bit far, but also a bit away from this subject. And my question is very, I think, naive, but also in the continuity of the previous question, is that these papers and these theories, which are super nice, are not really pursued with GCM studies, like with the climate, with the climate models. They are like forcing models, ice sheet models, but not really atmospheric and oceanic models. From, I mean, that's the feeling I get. And I was wondering if, because all these GCM studies are extremely nonlinear. So my question is that because on Mars.
Can I rephrase your question?
Sure,
whether,
sure. Yeah, I understand.
Didier, you show some small model, and the latest version of this small model going from insolation to ice age. Did you compare it to a global GCM to verify and to test it?
It can be very simple. So this is completely out of the scope of global GCMs for many reasons. First, the time scale.
Sure.
In atmospheric GCM, you need to compute the dynamic of the atmosphere about every 10 minutes or something like that. You cannot do that for millions of years. So it's not computationally feasible, not today, and probably never will be. So you need to do something simpler. Actually, there are some simple models who try to do that. So the paleoclimatologists have developed EMICS, Earth models of intermediate complexity. So from about 20 years ago, something like that. In particular, to solve this question of ice ages. So try to use a simpler representations of the atmosphere and the ocean and the ice sheets to compute ice ages. I think the best example today is probably the Ganopolsky model. So there's a paper by Villite 2018 in Science, I think, where they are simulating the whole quaternary with a Kleinberg model. So it's a 2D atmospheric model coupled with a 2D ocean model, coupled with a 3D ice sheet model. And
what is the outcome?
Well, it's always the same problem. When you know the answer, you get the answer. If you have a model with...
Yeah. In fact, we on Mars, we more than 10 years ago, we did some simulation with François Forger and my former student. We wanted to evolve to make the formation of the ice caps on Mars and the layers on the ice cap. And what we did was to run this intermediary complexity model for a while to get something stable and just derive from that some variation of some from some ice box that we had at the pole or at the equator. You just compute this and you do it for several situations, and then you propagate them because you could not, as you say, it cannot go over a million of years. But once you have the value, you propagate them through the orbital evolution, and then you get the evolution over several million years.
So there are indeed some strategies like that, trying to use the GCMs with some snapshots at some particular moments. So today, at the last glacial maximum, some different stages of the ice, and try to interpolate that and to use that. There are many techniques which are studied. So either in stupid interpolation or neural networks or emulators in general.
I would not say stupid, I would say simple.
Simple, exactly. Well, stupid is a sympathetic word for me.
But in any case, in all these simulations, I mean, for the Earth, for ice ages, in all those theories, there doesn't seem to be any, like, I would say, meteorological effect of nonlinear amplitude, which would be required to explain ice ages. Only like external forcing of the climate would be are invoked in these theories to really.
Well, yes, and I would say basically yes, because
okay.
The idea is that there's no well. In some way, the dynamics of the atmosphere is short. The memory of the atmosphere is short, and after a few weeks, you can forget the initial conditions, and possibly there are some multiple equilibria in some parts of the atmosphere, but usually it corresponds to phenomena which are on the monthly or eventually annual time scales, but not much than that. If you put the ocean, you can get longer time scales. And actually, in paleo records, you have variations, climatic variations at thousands of years time scales, and that probably involve the ocean, the deep ocean. For glaciations, Heinrich events and things like that, there's a role for the dynamics of the ocean. But on a 100,000 years time scale for the ice sheets, I would say probably not.
Okay.
Some discussions on the role of a carbon cycle. So the carbon cycle could have some role into the story for the Earth again. But I don't think the details of the atmospheric circulation should matter.
Linda, you raise your hand.
Wonderful talk. Thank you so much, Didier. It was a wonderful talk. I wanted to come back to the 100,000-year cycles again. And I would like to know your opinion about the potential role of the obliquity modulations. Since, I mean, you started the whole conversation saying that, you know, insolation is dominated by the obliquity, and then you pivoted off of that into the eccentricity, and you didn't talk about obliquity anymore. Do you think there's no role anymore for it to play? Yes,
that's the answer, I would say. I think it's clearly visible in the data. So if it's in the data, it has to be true.
Well, you know that the past 500,000 or million years,
but it should work the same. It should work the same. I mean, so quaternary is only 1 million year long, so it's the modulation of obliquity is 1.2 million year. So it's difficult to.
No, but there's another modulation at 100,000 years, 98,000 years.
Okay.
Yeah. And so, you know, as it approaches the present, the eccentricity, well, actually the first derivative of the eccentricity and the modulation envelope of the obliquity, they synchronize. So nobody has, that has sort of been not discussed at all. If everything is okay, you know, with eccentricity only, that's okay. But nonetheless, there's very little precession, at least, well, in the oxygen isotopes, to generate the 100,000 years. But there's a lot of obliquity. So I'm still, you know, I still wonder.
Yeah. So I don't know. That's my I would say my point of view is much more to try to think in terms of insolation forcing, and to use insolation forcing, we know, and even if we don't quite agree on which forcing would be critical for the ice sheets, so whether 6 months, 1 month, or whatever. So there's of course some discussion on what is the actual forcing on the ice sheets, but I'm not sure the quaternary is long enough in some way to discuss what's the role of the different parts of the astronomical periodicities, and that's why if I want to see the resonances or things like that, then probably I have to look at much longer timescales. I didn't thought too much on this question, so I don't.
Okay, thank you.
Okay, any other question?
I've got one.
Yes, can you present yourself, please?
Yes, hello, I'm Richard Hester. I'm a PhD student at George Mason University. I'm working with Professor Hinov here, partly, though I'm in the physics and astronomy department. One thing I wanted to say is just thanks very much for the wonderful talk. I really particularly appreciated the historical perspective that you began with. I find that really, really helpful to, you know, put into context what we're working on in the present day. The next thing was just a question back on your, you had an equation you put up for what's happening with the carbon over time, and you have 3 terms in there. One had to do with the weathering, yes, and the organic matter and the precipitation. And I wonder, is it, I have some background in working with oceanographers, and I've seen them work on this type of problem, and I'm wondered, can you still have that mechanism work if you just limit it to the ocean reservoir as giving out and taking in carbon? Or is it not enough to just have that?
I'm not sure I understand very well your question, but indeed the main reservoir of carbon which will interact with the atmosphere is the ocean. So when I talk about surface carbon, I talk mostly about the ocean. Actually, that's that's
Yeah. So what I'm getting at is if you eliminate that volcanism term,
yeah.
does it mess up everything, or do you still get generally the same results? Or do you know?
Well, volcanisms are the only input of carbon in the system, so I cannot eliminate them. It's a flux and reservoir problem. So the input is from the interior of the Earth. If you stop the volcanism, then there's no more carbon at some point. So I cannot do that.
Well, maybe a question of time scale. I guess I'm thinking on shorter time scales. You know, the carbon gets stored in the ocean for some amount of time, inaccessible to the atmosphere.
Yeah, but I
not
assume
causing
that
any greenhouse effect,
yeah.
and then it gets released from the ocean sometime later.
So your question is about the partition between ocean and atmosphere. Here in this model, I don't discuss that. I assume that ocean and atmosphere are in some kind of equilibrium, chemical equilibrium. And I'm only looking at the global carbon content in the ocean plus atmosphere plus everything which interacts rapidly with them, which is vegetation, for instance. So this is what I call a surface carbon, in contrast with deep carbon in the inner Earth, in the Earth mantle. So the question of the carbon between the atmosphere and the ocean is important for interglacial timescales, for instance, because you cannot use these fluxes. These fluxes are quite small, and the time scales are long. And on the 100,000-year time scales, you cannot change the carbon content sufficiently with this kind of mechanisms. So you need to talk about the partition between ocean and atmosphere to explain ice ages, for instance, but with the carbon cycle. And then you need to talk about ocean circulation. But here I'm looking on a much longer time scales, and I believe there are some changes in the surface carbon budget.
Okay, yeah, thank you again for the great talk.
Okay, thanks. I see that Linda, you have your hand raised, but probably you forgot to. Yes, and Marcia, you.
Yeah, I'm Marcia Brisson, and I'm at George Mason working with Linda. And I just had a very brief question about making your models and maybe trying to break your models, and the thought that there's a maximum ice depth that kind of starts the deglaciation. Do you feel that gives any insight into snowball Earth conditions?
Snowball Earth.
Snowball Earth. Well, I would not use a quaternary ice age model to talk about snowball Earth. Because as you have seen, it's mostly based on quaternary observations in some way. I'm taking the data and try to extract the physics from that. I would not believe this might apply in some way to snowball Earth. Maybe, but probably not. I'm not sure I understand I answer your question, but.
Yeah, no, I just was, well, it's very interesting that you think that
if you talk about astronomical changes during snowball Earth, I think there were some papers on that. So maybe during the snowball Earth there were some astronomical variations. So variations in the extent of moraines in some regions of the snowball Earth. And then, well, maybe. In any way, the threshold I'm talking about, it's very specific to quaternary ice ages, probably. It's, well, my opinion, so I skipped a few slides. I can show you. I like the idea to explain terminations with CO2. And I mentioned briefly why. And the reason is that CO2 increases before the melting of the ice. So during terminations, the Milankovich theory doesn't work so well. That's my starting point, and that's, I think, still an open question. And in this model, the idea basically is that you can store CO2 in the ocean, so keeping the net budget constant for ocean plus atmosphere, but you can put more carbon in the ocean, so work on the ocean atmosphere partition. If you change the circulation, and actually the bottom ocean circulation, it originates mostly around Antarctica on continental shelves. And what happens at the glacial maximum? Basically at the glacial maximum, there's no continental shelf anymore because the Antarctic ice sheet gets larger, and there's no room left for brine formations, what oceanographers call these ice salt factories. So you have the sea ice, which is blown away by the winds, and a lot of salty water which accumulates on the continental shelves, and this can help, this can produce bottom waters. And this happens today on the location where you have the stars. The reconstruction of the limit of the Antarctic ice shelf at the glacial maximum, it's the black dotted line, which tells you that there's not much room left for this kind of bottom water formation. And so in this kind of model, I am just assuming that when the Antarctic ice sheet grows up to the limit of the continental shelf, you switch the formation of deep bottom waters, and you can release carbon into the atmosphere, therefore triggering the glaciations. I think there's some truth into that. At least it's compatible with data.
Okay.
But
Thank
it's
you.
specific to this situation of the quaternary, probably not applicable to snowball. Sorry.
Okay, thank you.
But what is probably applicable in the global glaciation is in the snowball Earth is the fact that you have radically two time scales that are different for glaciation and for deglaciation. That's it. But don't you think so, Didier?
Yes, it's actually in some ways well, there are several time scales involved in the snowball Earth. The most dramatic one is the freezing of the ocean. So that's the fast time scale, just is to cover the ice, the ocean with ice, and this only takes a few years. In a few years, you can change the color of the planet from blue to white. If you cross the threshold of there's a threshold, there's a multiple equilibria in the global budget of the Earth, and people have done that with GCMs, and when the sea ice cross some limit close to the tropic, then you freeze everything in just instantaneously, I would say, in a few years. So that's the fast time scale, the most dramatic time scales for the snowballers story. And it's the same thing in the other way. So if you warm the planet enough to start the deglaciations, then the deglaciation itself, the deglaciation of the ocean, will just occurs in the matter of years. So extremely fast for the ocean. For the continental ice, of course, it's much longer.
Okay. Are there any question? Any other question in the audience? time to know everything about the Ice Age or the carbon cycle. So it seems that everything is clear for everybody. So thanks again, Didier.
Thank you for the invitation.
And,
Thank you very much.
And I'm afraid I cannot announce the next talk because I don't know yet what it will be and when it will be. I'll have, if you have any suggestion, please feel free to send this suggestion to me. Okay, and so bye to everybody, and I hope to meet you soon again.